So, what happens when you take one of the most famous ideas in all of physics, Einstein's Nobel Prize winning concept, and you try to apply it to its spooky twin, antimatter? Well, that's what we're doing today. We're going to go on a journey from the normal, everyday world of electrons into the really strange realm of positrons. And the big question is, does one of science's most perfect rules still work when you hold it up to a mirror? You've probably heard of the photoelectro effect, right? It's a classic. Light hits a piece of metal, and poof, an electron pops out. It's totally fundamental to quantum mechanics. But here's the thing. Physics loves symmetry. It's built on it. So that leads to the one big question that's going to drive this whole explainer. If it works for an electron, shouldn't the exact same thing work for its antimatter twin, the positron?
Okay, so before we can even get to the antimatter version, we've got to make sure we're all on the same page with the original masterpiece. The elegant idea that actually won Einstein his Nobel.
And what's so wild about this timeline is, well, the timing. Einstein figures out the photoelectric effect way back in 1905, but the positron, the anti-electron, it wasn't even an idea until Paul Dirac predicted it in 1928. Think about that for a second. The original theory never ever had to worry about antimatter because for all anyone knew, it didn't even exist. The process itself is just beautiful in its simplicity. It's really just 3 clean steps. First, bam, a particle of light, a photon, smacks into a metal surface. Then it transfers all of its energy to one single electron. And finally, if that photon was carrying enough energy, if it packed enough of a punch, that electron gets kicked right out of the metal, ejected. And right there, that's the revolutionary part. I mean, before Einstein, everyone just thought of light as a wave, right? But he came along and said, no, it's also made of these tiny little packets of energy. He called them quanta, which we now know as photons. And this idea that energy isn't continuous, that it comes in these discrete little chunks, that's the key to making this whole thing work.
Okay, here's a good way to think about it. Imagine the incoming light has to pay a fee to unlock a gate and free the electron. That's pretty much what this famous equation is saying. The total energy of the photon gets spent on 2 things. First, it pays that escape fee to open the gate. Physicists call that the work function. And then, whatever energy is left over becomes the electron's getaway speed. It's kinetic energy. It's simple, it's elegant, and yeah, it's Nobel Prize-winning stuff. All right, so we've got our foundation. We understand the classic version. Now, let's step through the looking glass. If physics really is as symmetrical as we think it is, what would the antimatter version of this effect even look like?
So first, let's meet the star of our show, the positron. It is the electron's perfect twin in every way, except it has a positive charge. It's the most basic piece of antimatter you can get. But there's a huge catch, right? The moment it meets an electron, they both just vanish in a flash of energy. That's annihilation. And trust me, that's a massive complication we're going to have to deal with. So, why do we even think this antimatter version should exist? Well, it all comes down to this really deep, fundamental rule in physics called CPT symmetry. Think of it like the ultimate cosmic opposite day rule. It basically says that if you take any physical process and you do 3 things to it, flip the charge, flip the geometry like a mirror image, which is parity, and run time backwards, the laws of physics should be exactly the same. It's this core belief that tells us an antimatter world should play by the same rulebook as ours. Okay, so if we just run with that symmetry idea, our first guess at an equation for this would just be a simple mirror image of Einstein's original. The photon's energy equals the kinetic energy of the positron that gets kicked out, plus some kind of positron escape fee. It seems super straightforward, right? Well, it's not even close. And this is where things get really, really interesting. See, a positron trying to exist in a world made of normal matter, it has a bunch of problems that an electron just never has to think about. That simple, mirrored equation just doesn't work because it completely ignores 2 giant problems that are unique to antimatter. The first one is pretty obvious, that constant risk of just annihilating. But the second one is even weirder. It's the chance that our positron isn't even free to begin with. It might be trapped in this bizarre temporary atom with an electron, a state they call positronium.
Yeah, this exotic atom is called positronium. Just picture a hydrogen atom, okay? But instead of a proton in the middle, you have a positron, and an electron is orbiting it. It's this incredibly unstable, self-destructing little system. So if our positron starts out locked in this state, the photon's energy has a whole other job to do. Before it can even think about freeing the positron, it first has to spend some energy just to break this fragile atom apart.
And then, of course, you have the biggest problem of all, annihilation. The very instant a positron touches an electron, poof, they can both just vanish. This means our positron, the one we're trying to eject, might not even make it out. It could get zapped before it fully escapes, losing all that kinetic energy we were trying to give it. It's like a built-in energy tax that the normal photoelectric effect just doesn't have to pay.
So the takeaway here is pretty clear. We need a totally new equation, one that actually takes these unique antimatter problems into account. So let's build it, piece by piece. Okay, step one. We've got to start somewhere, right? So we'll begin with the simplest possible case, a perfect, clean mirror image of Einstein's original formula. This assumes our CPT symmetry rule is absolutely perfect. This is our baseline. Now, for step two, let's add our first new wrinkle. We're going to add a term to account for that positronium problem. You can literally think of this as the breakup fee. It's the extra energy the photon has to spend just to tear that little electron-positron pair apart before it can get on with its main job. Okay, step three is where things get really cool. Physicists add this fascinating little term, delta CPT. What is that? Well, it's basically a placeholder for the unknown. We're assuming CPT symmetry is perfect, but what if it isn't? What if there are tiny little cracks in that mirror? If they exist, they would show up right here. Measuring this would be like opening a window to brand new physics. For now, we'll just assume it's zero, but it's there just in case. And finally, step four. We add the last piece of the puzzle, that energy tax. And notice, this term is subtracted. It's a minus sign. That's because it represents all the energy that just gets lost, drained away, if the positron annihilates before it can make a clean getaway. It's this constant risk that makes the whole thing just a little bit less efficient.
And there you go. That's the whole shebang, the complete theoretical formula. On one side, you've got the energy coming in from the photon, and on the other, wow, you have not just the positron's escape energy and speed, but you also have the breakup fee for positronium, that little placeholder for new physics, and the energy tax for annihilation. It's Einstein's beautiful, simple idea, totally supercharged for the weird, weird world of antimatter.
Okay, I know what you're thinking. This is a really cool thought experiment, but why? Why go to all this trouble? What is the actual real-world point of figuring all this out? Well, it turns out the implications are huge. This is not just from academic curiosity. It's a powerful tool for probing the very foundations of physics. If we could actually measure this effect, it would give us one of the most precise ways ever to test that CPT symmetry rule, to see if there are any cracks. And practically speaking, it could help us get way better at trapping and controlling antimatter. That's the groundwork for future tech we can barely even imagine right now, things like new materials or even new kinds of medical scans. And to show you this isn't all just abstract math, check out this number, about 6.8 electron volts. That's how much energy a photon needs to have to break apart a single one of those positronium atoms. That's not a guess. That is a concrete physical number. It gives scientists a real target to aim for, which means this whole theory is actually testable. And that really brings us to the final big idea here. You know, Einstein's original discovery basically blew the doors open for quantum mechanics. This antimatter version, it forces us to look right at the deepest, most fundamental symmetries of the universe itself. If we could run this experiment, and if we found that delta CPT term wasn't zero, that would be proof that the mirror between matter and antimatter isn't perfect, that it has a tiny crack. And that just leads to the biggest question of all, doesn't it? What other secrets are hiding in that crack?